Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be talking about the second law of thermodynamics, which is really going to tell us when a reaction will occur. And the big take-home point of this is that turns out reactions only occur if we bring a little bit of disorder to the universe. Now, one of the big things here is that so far we've only been focusing in on what happens inside a system. And we've seen plenty of reactions where the system can become more or less disordered. But it turns out the universe doesn't care about the system, it cares about the universe, so everything. So we can express this idea that spontaneity will only depend on what's happening inside the entire universe using what's called the second law of thermodynamics, which essentially says that a reaction only occurs if the entropy of the universe increases. And we've kind of been leading up to this all along. We've seen this from the start, that in order for something to happen, there has to be more possibilities. There has to be more microstates. Now, when we're talking about whether or not something will occur in total, it doesn't matter where those microstates are being generated, inside the system or in the surroundings. So we can kind of express this same idea by splitting up our entropy of the universe into two parts: the system, which is everything we care about, and the surroundings, which is everything else. So if I want to try and figure out whether a reaction will occur, I have to go ahead and figure out how both are going to change. So let's go ahead and take a look at a classic example, the melting of water, or melting of ice to form water. So in this case, in order to figure out whether the reaction will occur, I have to look at the entropy of the universe. And this is a really good example because this is a reaction that we know can generate water or ice or both at once. And we can see this by looking at the entropy of the universe. If the entropy of the universe is greater than zero, this reaction is said to be spontaneous. And the idea here is it spontaneously moves forward. It wants to produce the product. So big thing here, entropy of the universe is positive, we have a reaction. On the converse side, if the entropy of the universe is negative, this means that it is no longer favorable to generate our product, in this case, liquid water. However, remember, any reaction is going to be a two-way street. So if it isn't favorable to produce the product, it means it will be favorable to produce the reactant. So under these conditions, if I have any water present, it won't be present for long as it's going to form ice. And so here's a big take-home message. We can use the sign of the entropy of the universe to figure out whether the reaction goes forward, spontaneous, or backwards, non-spontaneous. However, what happens if entropy of the universe doesn't have a sign at all? What if it's zero? At this point, the reaction is said to be in equilibrium. The major idea here is the reaction is going both forwards and in reverse. So this is the reason it's also called a reversible reaction. Equilibrium essentially comes from the idea that everything is equally present. So if we think about something like ice, at high temperatures, it melts and produces water. At low temperatures, it will stay as ice. However, at 0 degrees Celsius, we reach that wonderful point at which both species are equally present. And so if I know how, as a result, if I know my entropy of my system and surroundings, I can predict the sign of my entropy of the universe. And this will help me dictate what direction the reaction works. So let's go ahead and try and figure out how I can determine both of these signs. So what's my entropy of the system? What's the entropy of the surroundings? So the system we're actually quite familiar with. This is going to be any way we order or disorder the system. So this can be things like a chemical reaction, may end up, say, like the generation of ice, help order my system. Or it could be like melting of ice and it disorders. Or it could be something like producing a whole bunch of gas. Whatever it is, we've actually figured out how we can numerically calculate this value. The surroundings are a little bit more complicated because we're assuming that no matter is coming in or out of the system, because if it did, that's still part of the system by definition. So as a result, the only way my surroundings are really going to interact with my system is in the form of heat. And we saw this previously, that if I heat a system, I end up increasing the disorder inside that system based on temperature. And that means the same thing goes in reverse. So I can figure out how the entropy of the surroundings changes based on how much heat has entered or left the surroundings. However, it turns out that this only is going to be true under these reversible conditions. And the reason why is because heat is a path function and entropy is a state function. So just like we had to do with enthalpy, we have to constrain our definition of what type of heat is entering or exiting the system in order to get a good definition. So for enthalpy, we assumed constant pressure. For entropy of surroundings, we're assuming reversibility. However, as we also know, at higher temperatures, that heat has less of an impact. At low temperatures, it makes a big impact. So we're also going to assume isothermal conditions because, well, I don't want to have to deal with a changing temperature. Now, here becomes a fun part, is when the system is reversible, it turns out that the entropy, the heat entering the surroundings is going to be the same exact thing as the amount of heat leaving the system. So we can express the change in entropy of the surroundings based on the net amount of heat leaving, thus the negative sign, the system, and the temperature of the whole apparatus. So then what we can do is say, well, turns out that if I'm under isobaric conditions, then the heat is the same thing as the enthalpy. So we can actually lose the dependence on reversibility and switching it out for dependence on being constant pressure. So it turns out for any constant pressure and constant temperature system, we can actually figure out the change in entropy of my surroundings based on essentially how much heat left the system and the temperature. So under these conditions, I actually have a much more convenient way of talking about how the entropy of the universe changes. It's going to depend upon how much I order or disorder my system and how much heat my system lost or gained. And again, with a dependence on the temperature for figuring out how much that heat matters. So as a result, a reaction tends to be favorable if I have more entropy, an increase in entropy in my system. Positive sign on my entropy of the system gives me a positive sign on my entropy of the universe. However, if I have an exothermic reaction, what ends up happening is that I have a negative enthalpy, which will also be favorable as it's going to disorder the surroundings. Heat is lost from my system, meaning that I have a whole bunch of heat entering the surroundings and making them way messier. And so this is the reason why things like making an ordered crystal or things like photosynthesis, where I make nice, beautiful sugar, these decrease the entropy of my system, but they do so because I made everything else messier. So this essentially says that while I can't make the universe a more ordered place, I can essentially use the same strategy any kid does. I can make my room more ordered by throwing everything in my closet and not worrying about it. And that's really what ends up happening in thermodynamics. And again, it is worth noting that many times these two forces are going to be at odds. I can make my system more ordered, but if so, I make the surroundings disordered. I can essentially cool my system, so end up losing heat or gaining heat. I can heat my system, I can end up gaining heat, but I have to do so by making the system more disordered. However, again, in these cases, what really will determine which one is more important is going to be the temperature of the reaction. Temperature essentially figures out the importance of that heat component. So what this helps illustrate is the counteracting forces. And a good way to look at this is with a classic example, again, returning to melting of ice. So we know that this process has a positive entropy because I'm going from a nice ordered crystal to a disordered liquid. However, we also know that this process has a positive enthalpy of fusion. In other words, I need to have heat come into the system to make this reaction proceed. Well, the question is, when will these two forces counteract? Well, they're going to counteract when both phases are equally present, when it's at equilibrium. So when the entropy of the universe isn't changing. So that would be 0. At this point, I can set the entropy of fusion equal to the enthalpy of fusion over temperature. So again, you'll note that a system can only reach equilibrium when both my entropy and my enthalpy share the same signs. And we're going to return to this point fairly frequently. So one of the other useful parts about this is that if I end up knowing the enthalpy of a reaction, because again, we determined how we could measure that last semester, and I know the temperature at which the system is at equilibrium, which is fairly easy to do with processes like boiling or melting, then I can figure out the entropy of a phase change. And this is really important because remember, we needed to figure out entropies of phase changes in order to get our third law entropies. Once we get those, we can figure out the entropy of any reaction. So, for example, if I'm looking at water, we know the enthalpy of fusion. We know the melting point, which is again 0 degrees C or 273 Kelvin. Then using this, I can figure out the entropy of fusion, about 22 joules per mole Kelvin. Again, I do want to illustrate the units on entropy, a little bit awkward. Most of the time, we're going to be using molar entropy. Good way to think about it is this is the amount of energy it would take to make the reaction more favorable. So next time, we're going to try and find a good solution to dealing with the fact that currently we're evaluating the favorability of a system using 3 different types of entropy. Let's see if we can simplify our notation a little bit more next time as we talk about Gibbs free energy. Until then, take care.